All right. Hi, everyone. Let's go over the Chapter 12 worksheet, which I've put onto Canvas for you guys. This chapter is on mass spectrometry and infrared spectroscopy. And as I speak, we've covered this entire chapter. So one of the possible question formats that I've told you about for mass spectrometry would be like this one, which actually this very question is in your class notes in that PowerPoint document. So I'll show what you need to know in order to solve a question like this. This is not the only possible question format for mass spectrometry. I might also ask you a matching question with several different spectra and several different structures. But this type of question asks about fragmentation, and you will need to know something about fragmentation also in order to answer some of these questions on the active homework. So basically, this is how the question stated. It gives you the spectrum. I've given the structure. And so you need to know, if necessary, how to convert a linear structure like this, at least in your mind, into a more typical looking structure that looks like this. That should be something that I expect you can handle after organic 1. And the question says, give the structures corresponding to exactly 4 fragment peaks other than the molecular ion, which, by the way, the spectrum gives you right here. So we can't use that peak at 146, that's the molecular ion. Also, other than the fragment in the example given. Here's the example given. Note well the format of the answer. We're giving the structure of a fragment that has a plus charge. Remember, in order to be visible on a mass spectrum, a species must be charged. So we're putting a structure that has a plus charge and then the mass of that structure, which we get just by adding up the masses of the most common isotopes of all of the atoms in the formula. This has 2 carbons and 5 hydrogens. 2 times 12 for the 2 carbons is 24, plus 5 for the 5 hydrogens is 29. So we wrote the structure, then said M over Z equals, and then the total mass of the fragment. So we can't use that fragment either, but we can certainly see that peak. Here it is right here at a mass to charge ratio of 29. So we need to come up with 4 other fragment peaks besides the peak at 29 and besides the peak at 146. That's the molecular ion. So can we identify 4 other peaks besides those 2? That's what the question is asking us to do. And in class, we said that in a mass spectrometry experiment, the molecule is going to undergo fragmentation at every single possible bond. Every possible bond that can break will break and will lead to a fragment. We can see how the fragment with a mass of 29 came about. It came by breaking that bond and giving a 2-carbon piece, an ethyl carbocation. We could also imagine breaking that bond and giving a 1-carbon piece. That would give us CH3 plus. Now, CH3 plus is not real stable, and so it's not always possible to see it. But if we do see it, we will see it at a mass to charge ratio of 15 AMUs, 12 for the carbon and 3 for the 3 hydrogens. So do we see a peak at 15? Well, we do. Here's 25, 20, 15. There is a small peak there. So we can put that as one of the answers. That's one of the fragments that we can put. So that takes care of one of the 4 answers that we need. Where else could we break a bond? Well, in the actual worksheet itself, where I give hints on where to start, I mention having the compound undergo a typical alpha cleavage, like we talked about in class, which means that you break the bond next to the bond between the carbon and the heteroatom. Heteroatom means something other than carbon or hydrogen. So here's our carbon-sulfur bond. We'll break the bond between carbon and sulfur. And of course, we could have done that in the other side of the molecule too. The molecule is symmetrical. So let's see what that gives us. If we break that bond there, then that's going to lead to a fragment with a plus charge on that carbon. That's only one way to draw it. This is a resonance-stabilized carbocation. We showed some examples of this yesterday in class. And so another way to draw the fragment would be by putting the plus charge on sulfur, like that. You can draw it either way. Both are equally acceptable. Both are equally safe. Neither one of these answers is any better than the other. Pick one. Pick exactly one. They're both equally correct. Now, active seems to prefer the resonance form that has the double bond between the carbon and the heteroatom. I don't care. The rules for drawing a resonance-stabilized species are you pick whichever one of the resonance forms you want. They're all equally correct, equally safe, equally good. And so now all we need to do is add up the mass of this fragment and see if we can find the peak for it. So we've got 1, 2, 3, 4, 5 carbons. We've got 1 sulfur, and we've got 2, 4, 6, 8, 11 hydrogens. So it's going to be essentially C5H11S+. So 5 times 12 is 60 for the 5 carbons, plus 11 more for the 11 hydrogens. 60 plus 11 is 71, plus 32 for the sulfur. 71 plus 32 is 103. Do we see a peak at 103? Yes, we do. It's right here. So we would show that structure, and we would say either of those two structures, and say M over Z equals 103. And that would be another acceptable answer. And so let's see if we can find any other peaks. It's interesting that we have all these peaks that seem evenly separated. And I'll bet you anything they're all separated by 14 AMUs. And remember, 14 AMUs is CH2, 12 for the carbon plus 2 more for the 2 hydrogens. And there's any number of places that we can lose a CH2. We could imagine losing a CH2 from this side and having the plus charge on sulfur. Oh, geez. Probably still not going to like that, but we'll go with it. So that's one possible structure. You could also have lost the carbon on the other end, I suppose. But this fragment or any isomer of that fragment will all have the same mass. It'll basically be whatever the mass of this is minus 14 because we've lost CH2. So 103 minus 14, let's see, that would be 9389. Is there a peak at 89? Let's see, 100, 95, 90, 89. There is a fairly significant peak there at 89. So that's another answer that we can put. So we've got 3 of the 4 answers necessary. What if we went on the other side? What if we added another CH2 back onto this? In other words, what if we had this fragment? Just an additional carbon, something like this. And I bet that wouldn't be a terribly stable carbocation, by the way. Probably it would undergo a 1,2 hydride shift to make CH3 over here into plus charge over here, which would be resonance stabilized. So you could draw it that way too if you wanted to. That's not a resonance form of this. That's an isomer of that structure that you get by a 1,2 hydride shift. And so in turn, that structure could also be drawn like this with a double bond. However you choose to draw the structure, either as one of these two resonance forms or as this species that we have before the 1,2 hydride shift occurs, they all have the same formula. They're all C6H13S. Let me just double check that. 2, 4, 6, 8, 10, 13. Yep. And so the molar mass of that fragment, whichever way you draw it, is going to be 14 more than the mass of the 103 fragment. So this is going to be 103 minus 103 plus 14 is 117. Let's see if we can find a peak at 117. 125, 120, 987. Yep, there it is. And there's another one over here that we could identify. We could have identified any of the propyl carbocations at m over z equals 43. The isopropyl and propyl carbocations are there. We could have picked the big peak at 57, which is going to be all of your butyl carbocations. There are many other correct answers, all of which I've listed in the answer key to the worksheet. So you have all of these possible answers. There are many, many, many possible answers. All we needed for this question was any 4 of them. So that's pretty much it for the mass spec problem. That's how to approach a problem like this. If instead you get a matching problem, then you'll approach it pretty much the same way that we would approach a matching IR spectroscopy problem or a matching NMR spectroscopy problem. So that's pretty much it. Any of those 4 answers would be just fine, or any other set of 4. So let's move on to the IR spectroscopy question. We've got 4 spectra and 6 structures, and our goal is to match each spectrum to one of the structures. And again, just as with the mass spec, I've given you some hints on where to start. What you want to do is look at the spectra and see if you can find a functional group with a really obvious signature. And the ones we went over in class all have something really obvious. And I think probably the most obvious one is this spectrum C. This has this really broad, smooth, beautiful parabolic shaped peak at about 3,300, 3,350, 3,400 wave numbers. And in class, we said that's the OH stretch of an alcohol. None of the other spectra has that type of peak. Only spectrum C does. So the answer for spectrum C must be an alcohol. Let's see if we have any alcohols in the structures that were given. Yes, structure X is an alcohol, and it's the only one of these that's an alcohol. Compound Y is a carboxylic acid, not an alcohol. So the answer must be compound X. Let me just make sure my answers match. Looks like actually they don't. Looks like I'm going to have to upload the document again. Spectrum A is X, not Y, which means spectrum C is not X. So we'll fix this, and then we'll re-upload that, and we'll upload the correct version. Oh, wait a minute. No, we're fine. That's not spectrum A. That's spectrum C. Right, so spectrum C is X, as the answer key correctly has. Let's move back to spectrum A. Spectrum A also has a couple really obvious signatures in the IR spectrum. It first of all has this really ugly broad peak that pretty much obliterates most of the higher frequency end of the spectrum. That's something we talked about in class. That's the OH stretch of a carboxylic acid. We also have this really strong peak at around 1700. That might be at about 1720. And so that's a carbonyl stretch, C double bond O. Of course, the carboxylic acid has a C double bond O in it. There is only one carboxylic acid among all 6 compounds. So it must be compound Y. We will get to an example just now of what if there are 2 possibilities and how do we narrow it down. We'll get to that. There's an example like that in here. In fact, I think we're about to come across it in spectrum B. Spectrum B has a couple of things. First of all, we again have a really strong peak at a little above 1700 wave numbers. That has to be a carbonyl, C double bond O. How many carbonyl compounds do we have left? Well, we have 2 of them. We have these 2 aldehydes. One of the aldehydes has just alkyl carbons, and the other one has an aromatic ring. So let's see if we can see things that are indicative of an aldehyde. Certainly the carbonyl is. This peak over here is actually the aldehyde carbon-hydrogen stretch, but even if you don't know that, it's okay. You can still tell that from this spectrum and the examples that were given that we need to have an aldehyde. So the only question is, do we have an aromatic ring? Right? Because one of the structures, structure W, is an aromatic ring, structure V does not. They're both aldehydes, so it must be one of them. But is it the saturated one or the one with the benzene ring? Well, if we had the benzene ring, we'd first of all see carbon-hydrogen stretches at just above 3000 wave numbers. That was something we made clear in class. We would also see the aromatic overtone bands. Remember those small peaks, around 3 or 4 of them that you'd see at around 1900 or 2000 wave numbers. And when we look at the spectrum, I don't see either of those. All of the CH stretching frequencies are just below 3000 wave numbers, indicating that all of those hydrogens are attached to sp3 hybridized carbons, not sp2. Also, when I look for the overtone bands, I don't see any. It's completely flat in that area. So of the 2 compounds between V and W, spectrum B must be compound V. It must be this one, the one without the aromatic ring. So we've accounted for X, we've accounted for Y, we've accounted for V. The remaining one looks like either an alkane or an alkene or the other aldehyde. So let's take a look at it. Here's spectrum D. Immediately we can tell it cannot be the other aldehyde because there'd be a really strong peak around here at around 1700 wave numbers. There is none. So there's no carbonyl in this compound. There's no C double bond O. We can rule out the other aldehyde. The question is, do we have an alkane or an alkene? Those are the only other 2 possibilities. And when you look at the CH stretching frequencies over here, if you draw that imaginary line upward from 3000 wave numbers, you find there are some peaks just above 3000 wave numbers and some peaks just below 3000 wave numbers. Therefore, this compound must be the alkene. It has to be the cycloheptene, compound Z. Compound U, we don't have that spectrum, and compound W, that spectrum isn't here either. So we've accounted for all of them at this point. Spectrum A is compound Y. Spectrum B is compound V. Spectrum C is, I believe, compound X. Yes, that's right. And spectrum D is compound Z. So exactly like you have in the answers over here, Y, V, Z, X. So that's how you go about solving a question like that. You look at what you can find in the IR spectrum, what functional groups are present, and what could be even more important, negative information is also important, which is what functional groups are absent in that spectrum. What do you not see in that spectrum that would be there if the functional groups are present? And you compare to the structures that you're given, and you narrow it down based on what functional groups you can either see or not see in the spectrum. So that's how I would approach the material in chapter 12. Again, I don't promise that your exam will have exactly the same question format. But these are still good practice questions for the exam. You can also look at the practice exam, which is available on Canvas. And I go over the practice exam on my YouTube channel from this past term, fall 2024. That term, we only had 4 exams rather than 5. So there's going to be some chapter 15 and 16 material in the first review session. So you can ignore that for now. That will apply then to exam 2. Other than that, I hope this was helpful, and we will get this up on YouTube as soon as possible. Have a great weekend. Stay warm. We'll see you all on Monday. Wednesday. We have Monday off.